my homework 3 has two main parts. The first part was about tracking a recognizable tag in the world with a camera and knowing its pose and displaying the graphic. The second part was about taking multiple pictures with a phone of the same scene from different angles and building a virtual 3D model of the scene. Both parts assume that the camera is calibrated. Let me first explain to you the AR image tracking part of the assignment. What I did first was I loaded an image of a known pattern and found distinct features in it. Those features are centered around corners that are found by the feature detector BRISC. Then I wanted to find these features in my camera feed whenever the known pattern was displayed. I wanted to know when something in the camera feed looked similar to the known pattern. To do that, I ran the feature detector to the camera image to find all the interesting corners and their identifying descriptions. Then I used the matcher to tell me if the camera image showed the same known pattern. The matcher takes in features of the camera image and tries to match them to the features of the known pattern. When there is a match, it keeps track of what features in the known pattern correspond to what features and its location in the camera image. That's great. So now, when there are matches, I can compute where to place the visuals and make it look like it's connected to the plane. What I did is that I took the two sets of corresponding points and computed the transformation between them. That transformation, or homography, is then broken down into a rotation matrix and a translation matrix. That tells me the pose of the planar pattern in the camera feed. Now that I have its pose, I can project the graphics points in the same pose. To do that, I take the given 3D points of the graphic and project them into the 2D surface of the image feed. What happens there is that I made the 3D points into homogeneous coordinates and multiply each of those points by the extrinsic matrix, which is a rotation and translation, and then I multiply it by the intrinsic matrix. Finally, I normalize the vector to get its correct size when projected on the image plane. These 2D coordinates of the graphic are rendered and appear to always follow the pattern in the camera feed. Now the other part of the assignment is about creating a 3D model of objects in the scene. Multiple pictures from different locations are taken of the same scene. That scene contains a known pattern too. Using that information, I'm able to calculate the depth of features in the scene and create a 3D point cloud of the scene. Let me tell you about it. The first step was to compute the pose of each image in the scene. That was very similar to the first part of the video. I found text features, matched them, and found the homography. I again visualized the graphic on top of the known pattern. Next, I computed the pose of each image with respect to the first image, or reference image, and got the rotation and translation matrices from that. Once I knew the different images' relative poses, I wanted to find the same objects in the scene in each of the different images. I wanted to find features that matched between the reference image and the other images. Like in the other part of the assignment, I used a known pattern, but this time the pattern was the reference image. I then did the same operations to find the features and matches. Now that I had matches, I wanted to pick out only the best ones, so I filtered them based on whether they fulfilled the epipolar constraint. Then I filtered them once more by tracking whether the feature in the reference images was present in at least 3 other images. Those features that persist over multiple images provide a more robust measurement of their depth, so I kept those. Finally, I used the resulting matrix in a matrix called M. Each column represented one of the features, and each row block within a column represented an image that contained that feature. And the last column is of translations. Using total least squares minimization, I computed the depth of each feature point of the reference image. I then applied the depth of each of those reference image points and visualized a 3D point cloud of the scene.